Welcome everyone. Let's start off. The last class we have finished with the friction. Today we'll be starting with circular motion. Now in circular motion, we have three parts. One is the circular kinematics, then we have uniform circular motion and non-uniform circular motion. So let's see the first part, circular kinematics, and others do keep your cams on. So just like we defined, position, velocity, and acceleration, here you also define something. We define something called angular position. So you will see a lot of resemblance with kinematics, 1D motion. Angle is theta. So the angle made by the position vector with respect to the reference. That means you can take anything as reference. Let's say if I take a vertical line as reference, or let's just take this horizontal line as reference. And let's say the particle is going in some weird path like this. So if the particle is here going with some velocity, so this angle theta is your angle. You're getting it? Now see, it need not go in a circle. This is one thing people think, because circular motion, the angular position is defined only for circle. Circle is a very special case. You can actually define for any random curve. Right, after some time when it has traveled here, this will be the new angular position. So here you can see theta is continuously changing. So r bar need not be constant. But if something is going in a circle, it becomes more convenient. So r bar is your position vector and theta is your angular position. So for angular position, the magnitude of r bar doesn't matter. You can have small r bar or big r bar. The length of r bar can change, the direction can change. But angle is simply defined as the angle between the two things, the reference line and the vector. Yeah, polar coordinates are more suited. So polar coordinates is that only, r and theta. And again, in our portion, we don't have polar coordinates and all. We use it only for some few cases. So for angular position, so the magnitude of r bar is not required. No matter how big the vector is, that means you could have a vector this long, you can have a vector this small, all have same angle theta. R bar does not affect, so it's not needed. Clear? Pretty straightforward definition. So the angle made with the reference line. Then how do you choose the direction here? Again, same thing. If you remember, we use right hand thumb rule here. So we define something called angular displacement. If you remember, I mean, vectors, we learned something called pseudo vectors. So delta theta bar will be theta final bar minus theta initial bar. So if you rotate clockwise, this is the clock direction. This will be minus k cap. This will be into the plane. So this is how it is represented. You show it this with a cross. Suppose if you rotate anti-clockwise, we show it with a dot. The direction is plus k cap out of the plane. So what are we using here? We are actually using the right hand thumb rule. Where's this? So this fingers, right, is the rotation. So if you take your right hand rule, and if you make a curl of the fingers, if you make a fist, that gives you the rotation. The thumb gives you the direction. So curl of the fingers. I'll show an example. Curl of the fingers gives rotation. And thumb gives you the direction. Basically, this is your right hand thumb rule. You have to use your right hand. If you see in detail, we have done this in vectors. There, if you see, it is the same picture I used there. Pseudo vectors, actual vectors karke. So we take the curl of the fingers as a rotation and thumb indicates the direction. If you see, we have taken different examples also. So the thing is, whenever rotations are involved, the same thing. Yeah, angular displacement in true sense is not an actual vector. It gives a sense of rotation. If you remember why we define pseudo vector is also this is the reason. At every instant, the velocity is changing. So when this particle is going in a circle, at every time there's a different direction. It becomes very inconvenient. So we wanted something more convenient where you can define the direction with one vector. So when someone says 2 revolutions per second I cap, it means put your thumb in the direction of I cap and the fingers will give you the direction of rotation. Do you guys remember this pseudo vector stuff? So I'll just put this as a reference there. Page 84, vectors. So you can check it out. Huh? If you have a bottle nearby, if you take your bottle and observe that. So if you take a bottle, right? So if you want the cap to come out, I'll use the right hand thumb rule. So I want the cap to come out this way. If you're looking into my screen. So look at my right hand here. Okay, my fist is going this way. That means my rotation is this way. So if I rotate this bottle cap this way, it's going to come out. Same thing, you want the cap to go inside, so put your thumb down. So rotation is this way. So if I rotate this way, the bottle cap is going to become tight. Is that making sense? This is how all the screws work actually. When you want to open your water tap, must have confused, right? Anytime you get confused when you're opening a screw sometimes, you try to rotate in one direction, it becomes tight. Then you rotate in the other direction. So if you actually use your right hand rule, you can figure it out which way it is rotating. So the reason why we call it a pseudo vector is because the thing is actually not moving in that direction. So it only gives you a sense of rotation. So for example, let's say we have a particle, a reference line. Let's say this is like this theta initial or theta 1. Let's say this is theta 2. These are angular positions. So someone asks you, what is the angular position theta 1? So this is how you write in a vector form, pi by 3. And look at the direction. It is rotating anti-clockwise. So we put it as k cap. So theta 1 is pi by 3, k cap. Now, it does not mean the particle actually went in the z direction you're getting at. So put your thumb along k cap. That will be out of the plane, right? And the fingers will tell you how much you're rotating. And rotate your fingers by, or rotate the curl of the fingers, you should rotate by that, what do you call, 60 degrees. Curl of the fingers gives rotation. So you can also write this thing as anti-clockwise ACW. Similarly, if theta 2 will be, it is going in the opposite direction. So thumb will go into the plane. This will be pi by, let's call it pi by 6. Pi by 6 minus k cap, clockwise direction. Clear with this? So if you want to find delta theta, which is theta final minus theta initial, theta 2 minus theta 1, something of this sort, then this will be pi by 6. You should take with the signs. So the displacement will be pi by 2 minus k cap. So be careful with this. Huh? All these rotational quantities are pseudo vectors. They're not real. Clear with this? Again, why did we define this? Understand one thing. This pseudo vector thing is something which we created for our convenience. That is because when these things are going in a circle, you get infinite directions. We don't want to deal with so many directions. So we created one false vector, which will give you the sense of rotation. So just look at this. If you have a fan in your room right now, and if it is rotating, what is the direction of the fan ka rotation? Suppose if I show you like this, now if you look at my screen, right? Suppose if something is rotating like this, you're getting how it is rotating. What do you think will be the direction? So this is coming towards you, and then it is going away from you. Coming towards you, going towards from you. So take your right hand. So it's coming like this. So my fingers have to go in this direction. You're getting it? So thumb is pointing up. So we say the direction of rotation is upward, but it doesn't mean it is actually going up and down. This thing is simply going in the plane. Are you clear with this? So let's take some examples so that you get the hang of it. So you should definitely check out that pseudo force ka thing in case you are confused. Let's say this is X, this is Y, and this is Z. Let's say if you have a particle going in a circle like this. This circle is in YZ plane. Can you tell me what will be the direction of this? It's coming out from here. So this is out. At the bottom right, it is going in. I didn't draw it properly. So it is going in. This is going up and this is coming down. What will be the direction of that? So just imagine, see, you're sitting there now, you are the origin, okay? Your right side is x-axis. Try to visualize. Your right side is x-axis. Your front is y-axis. Up is z-axis. Are you able to visualize the directions? Your right hand is x-axis. You just stretch your right hand, that is your x-axis. Stretch your right hand and say that's your x-axis. You're facing right, that is your y-axis. Ceiling is your z-axis. So your circle is going in YZ plane. So your circle is actually going like this. It's going to the front and coming back like that. Are you able to visualize? So here, if you see the rotation, right, what is the direction of this? The fingers will be making a twist like this. It is rotating like this. It is going in and it is coming out from the top. At the top, it is coming this way and it is going this way. So this is your negative y-axis. This is minus y, this is minus x, and this is minus z. So what is the direction here? So it is coming out from the top and then going like this. So this is the direction, front and back. So if you take your right hand and make a fist, the fingers will point this way, isn't it? So your fingers are pointing towards the z-axis. So the direction of this vector is actually I cap. So for example, if something is rotating like this is how they will write. They will say the particle is moving 2 revolutions per second, I cap. It doesn't mean it is going in I cap. This is the direction of the thumb, and the fingers will tell you the direction of the motion. Let's say if I take one more. You guys need to visualize this in your room. It will help. You should do that. What if it's rotating like this? So here it is going this way, here it is going this way, here, this way, and this way. The particle is going like this in XY plane. And let's say 3 revolutions per second. And they'll ask you, what is omega here? What is the direction of this guy? Same story. Your right hand is x-axis, your front is y-axis. So it is going like this, huh? It's going in this plane. It's going towards y and then coming like this. So rotation, thumb is pointing up. So this direction will point up. So you write this thing as 3 revolutions per second, k cap. It doesn't mean the particle is going in z-axis. I hope that is clear. So whenever you deal with rotation ka directions, understand that is not the direction of the particle. The particle does not go in that direction. It simply gives you a sense of rotation. It's more of a convenience. Clear with this? That is one thing. So be careful with the directions and stuff. So when you take angular displacement, delta theta finally is equal to this thing. So this is your angular displacement. You have to take thetas with vectors, with the things. Now, if a particle completes one revolution, be careful, linear displacement is 0. Now, we will not call it displacement anymore. We'll call it linear displacement because there's a confusion now. So if you complete a circle and come back, linear displacement is 0. But angular displacement is not 0. Angular displacement is 2 pi. Getting it? So if you want 0 angular displacement, the particle should rotate in the opposite direction, meaning let's say one rotation you're making clockwise and another rotation you're making anti-clockwise. Then we say it is 0. Then it becomes 0. So this will be plus 2 pi and this will be minus 2 pi. So be careful. Linear displacement ka definition is the distance between the initial and the final position. That's your linear displacement. Angular displacement ka definition is the angle rotated with respect to the reference line. If you're rotating clockwise, you get one direction. If you rotate anti-clockwise, you get another direction. So if you want 0, then you should rotate clockwise once and anti-clockwise once. Then you get 0. Clear with this? Simple thing, but be careful when there's a displacement, because kinematics, we are so used to it now, we just make it 0. Yeah, that's a little bit about displacement. So this thing is similar to position. Next thing. Any doubt so far? I wrote, sorry, angular displacement is 2 pi. My mistake. That's not 0. If linear displacement is 0, angular displacement is 0. No, it's not right. It's 2 pi. My mistake.
सर कि जैसा वो ऊपर जा रहा है सर, it is rotating clockwise and also it is rotating anti-clockwise, then it will come to same location. So there,
Then it will be 0. Yeah. Then it will be 0. If you go front and back once and twice, then it is 0. Next thing, angular velocity. This is similar to your velocity. We call it omega. So this is simply rate of change of angular position. So omega bar is d theta by dt. If you see, it looks like v is equal to dx by dt. The average angular velocity is nothing but theta final minus theta initial by time. Just like what is average velocity? Displacement by time. So it is angular displacement by time. Delta theta will be integral omega dt. So this will be area under omega t graph. Like I said, everything you learned in kinematics will come. So theta का place में x, b का place में omega, a का place में alpha. So if you have a omega time graph, so the area above is positive, the area below is negative. If you take the area under the graph, you will get you the angular displacement. Similarly, if you take theta versus time graph, if you take a tangent, so in a theta time graph, the slope will be angular velocity. In xt graph, slope was velocity. So all the graphs, everything that you learned, you just need to replace omega with v and you will see something similar. Clear with this? Next thing. So if you consider particle going in a circle, with speed v. So if you take this angle to be theta, let the speed be v, and this distance is your arc length s. You know the formula for arc length, s is equal to r theta. Now if you differentiate both sides with respect to time, now remember here r is constant, so this will be ds by dt. If r is also changing, then you'll get dr by dt. We'll not get into it right now. So this is r d theta by dt. So this ds by dt is what? S is your tangential distance, the arc length. So ds by dt will be v tangential. So particles can have two different speeds. You can go this way, you can go this way. So then you'll go in some random path. Just like you resolve velocities in x and y, you can resolve velocities v tangential and v radial. Anyway, in most of the things that we have, we will only handle the tangential parts. This will be r into omega. So if you write the vector form, v tangential is given by omega bar cross r bar. Keep that in mind. It's a cross product. Maybe I'll use small r theta. That's your relation between velocity and tangential velocity and omega. So remember that v is not the total speed, it is only the tangential speed. If you actually look at the side view, the particle is going with velocity v this way, v tangential. This is your r bar. This is your omega bar. So omega cross r bar will give you the v bar. So here omega bar is a pseudo vector. V bar and r bar are real vectors. Yeah. Omega thing is simply like 1D motion we are converting it. Clear with this? There, so simple. What is omega? D theta by dt. Or what is omega? You can see V tangential by R. And what is V tangential? The velocity perpendicular to the R bar is called V tangential. So just to give an idea there, if a particle is not going in a circle, it's going in some random path. So you can actually split this velocity into two components. So this guy is going like this with V. So this can be split into two components. This will be V tangential. And this will be V radial. So V radial is responsible for changing the R Varka vector. Anyone remember where you have done something like this? Kinematics. Told you this will come again. Remember this? D mod R by dt. So a velocity will have two components. U cos theta is responsible for changing the length of the vector, and U sin theta is responsible for rotating the vector. So this U sin theta is your tangential velocity. So that will be a V radial and V tangential. When you're going in a circle, V radial will be 0. So if someone asks you omega at this instant, this will be V tangential by R, which might be changing because R is also changing every instant. Anyway, so that is a bit about it. Have a look at this. Clear? Let's see a question on this. So we have a particle here starting from 0, comma d. You're going with constant speed u in a horizontal line. And we have the observer standing at the origin. This is important. Huh? Where is the observer? Parallel to x-axis with speed u. Find the angular displacement. And angular velocity. At time t. As seen by the observer at the origin. For reference, you can take the y-axis as a reference for angle. Yeah, let's get this. Right, Samyak. Right, Srihari. Get the omega also. Try everyone. Then in case you're confused, what am I asking you? After time t, the particle will be somewhere here. So I am asking, what is this angle? Isn't it? The particle is continuously going forward. So the angle is continuously changing. The angle theta is changing continuously. So what is that angle after time t? And what is omega? Omega is the rate at which this angle is changing. Okay. Yeah, most of you got that angle. Get the omega. Arya, that looks right. Yeah, that is right. Yeah, all got the angle. Try. I'll give you another minute. Get that omega. Yeah, there are two ways you can do. You can go completely mathematically. So let's say after some time the particle will reach here. This distance will be u into t. This will be your r bar. This angle will be theta. This distance will be d. Tan theta will be ut by d. That was easy. So we get angle is equal to theta tan inverse ut by d. And what about the direction? It is, if you see, it is rotating clockwise. So we will say minus k cap. Right hand rule. Now, how you find omega? You can differentiate theta directly, but tan inverse ka differential we don't know. So let's differentiate tan theta only. Tan theta is ud by d, differentiate with respect to time. And we have done this kind of questions also. Remember where? Constant motion. When theta was changing. Tan ka differential will be sec square theta. Then we have to differentiate theta inside because it's a chain rule, theta dt by dt. This will be u by d. D theta by dt is omega. So this will be u by d sec square theta. Sec square theta is nothing but 1 plus tan square theta. And tan theta is ut by d. Substitute here. So you end up with ud by d square plus u square t square. Check. That's how you get it from differentiation. All clear with this?
Yes, sir.
Any other doubts? Others? How do we do this the other way? This is what we did in kinematics. So the particle is going in a circle. This was your r bar. This was theta. This is your speed u. This angle will be 90 minus theta. This angle will be 90 minus theta. So this component will be u cos 90 minus theta. That will be u sin theta. And this will be u cos theta. So u cos theta is your v tangential. And in this triangle here, this distance is d. Cos theta is equal to d by r. So r is d sec theta. So what is the definition of omega? V tangential by r. V tangential is u cos theta, and small r is d sec theta. This will be u by d sec square theta. Isn't it the same thing that we got, u by d sec square theta? Then you can simplify this, so you will get it. So this will give you omega at that instant. This idea there, we have seen this in kinematics, this one, page 41. Now this will be useful. You will see why. Because at calculus part now, if the problem becomes complex, you won't be able to understand. So let's say a question like that. Any doubts on this? So either you can do with pure calculus or you can use this logic, resolve the velocities and get V tangential. Next one, a particle is projected with u1 theta. Then it goes in a projectile motion. This is the origin 0, 0. I can ask as function of time t, but let's keep it simple. Find omega of the particle as seen by the origin when it is at h max. Let's get this. So particle is projected with u1 theta from the origin. So when it is at the h max, again see, when you say omega, don't think about circular motion. It need not be a circle. What is omega? Rate of change of angle. What is the angle? Look at this. When you're here, this is the angle. 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 You can clearly see the angle is continuously decreasing. That's it. Rate of change of angle is angular velocity. The particle need not go in a circle to get an angular velocity. Look at the previous problem is the best example. It is going in a straight line. And I defined angular velocity for this. So angular velocity doesn't care about the circle. So I know the chapter name is circular motion. So we'll be studying a very special case of it where things go in a circle. But you can define this omega and everything in general for any type of motion. Let's get this. Try, you got 2 minutes. Find angular velocity of the particle as seen by the origin. This is important. You should always tell who is looking at this. Because if you have an observer standing here, he will tell a different answer. Any other answers? Arc tan u sine theta by 4. How did you get that omega without any u, theta, nothing? U sine theta, you don't have any distance there.
Sir, u or theta to है ना sir? We are putting that.
No, it is wrong. Just think about the last question, how we did this. So at the highest point, this is your velocity. I hope everyone knows this, u cos theta. This is your r bar. So if you take u cos theta, this component, that is your v tangential by this distance will give you omega. That is the idea. Isn't it? I don't think I'll get a good answer. Let's see. See. So at the highest point, the particle ka speed is u cos theta. So from here to here, this is your r bar. This angle be alpha, this angle be alpha. Then this component will be u cos theta cos alpha. That will be your radial velocity. This will be u cos theta sine alpha. That is your v tangential. Basically, the velocity perpendicular to r bar. And we know this will be nothing but this is r by 2, which is half of the range. And this is your h max. So omega here will be v tangential by that r. This thing doesn't look good. So this r will be root over h max square plus r square by 4. And what is that sine alpha? Sine alpha will be opposite side, which is h max by root over h square plus r square by 4. So if you substitute everything here, we got u cos theta sine alpha by r. U cos theta sine alpha will be h by root over r square plus r square. Small r is also this, so this will become h square plus r square by 4. And you know the values of h and r. What is h? H is u square sine square theta by 2g. R will be u square sine 2 theta by g. I will leave it to you. You can solve it and see. Your numbers are given, you would have got it more easy, I guess. Are you getting anything good? It looks very weird only. So there, you can simplify that, and that will be your omega. You know all the values there. If numbers are given, like I said, it would have been more easy. Clear with this? If you try to do this with calculus, it becomes quite complex. You have to find that theta with time and then differentiate. Yeah, I could have got it, but yeah, lengthy. Any doubts on this? Let's see one more. Clear with this thing, Devanshi? Aditi? Advai? Yashvi? Vanshika? Clear with this? Tanishka? Sudiksha? Trishi? Srihari? Rudransh? Any doubts? Ovia? Clear? Next one. So let's say we have a particle going in a circle. This is another standard question. CET means or bits level question. Standard resolution, remember this. A particle goes in a circle with speed v. Radius is r. So we have two observers. One guy is in the center and one guy is on the circumference. Both of them are looking at a particle which is going in a circle with speed u. Find angular velocity of the particle as seen by A and O.
So both are always looking at the particle, right?
Yeah. Let's get this. Find the angular velocity of the particle as seen by O and A. So angular velocity will change depending on who is looking at it. The same particle, when different observers see, you get different answers. Get this is an easy one. I'll give you a minute. Clear? Let's see. Now, if you ask O to solve the problem, he will say, okay, this is my R. And this is already perpendicular. So omega as seen by O will be simply, so V tangential by radius, which is U by R. But for A, unfortunately, right, if you see, this is R bar, so it's not that straightforward, but there's a better way to do this. We use a little geometry there. So if you take this angle to be theta, this angle will be theta by 2. Did you learn that in school? You can prove that. If this is theta, if you remember, this is R, this is also R. So it's an isosceles triangle. So this is alpha, this is alpha. This will be 180 minus 2 alpha. So the total sum 180 minus 2 alpha plus theta must be 180. So 2 alpha is theta and alpha is theta by 2. So then we can use the definition of omega. So omega as seen by A is nothing but d theta by 2 by dt, the rate of change of angle as seen by A. So this will come out to be half d theta by dt. But we already know this omega O is nothing as d theta by dt. That means this is omega u by 2r. Are you getting how we did this? Now look at that same particle, even though it is going with the same speed, A will think it is going with half the rotation and half the angular velocity, and O thinks it's going with omega. So depending on who looks at the problem, you can get different angular velocities. This is something which you actually see it every day. Did you ever see this thing when you're going on your car or train? When you look at the ground, it looks like the ground is going faster than the tree which is far. Must have noticed it, right? Why do you think that happens? So think about it. Let's say you're going in a train. the train is going with a speed of 50 kilometers per hour. From relative velocity, let's say if you have a tree here, and if you have another tree here, technically speaking, both the trees are going back with 50 and 50. So in your frame, you should technically see both the speeds, both the trees ka speed is 50 backward. But what happens is this, in time t, they will travel same distances. But look at the angle subtended. Your angle from here, it went to here and it went to here. Did you see what happened? The tree which is closer will get a bigger angle compared to the tree which is far. So we humans, right, what we see is not lengths. We can never see what is a length. You can never see what is a speed. All your life, what you're seeing is always angles. We are actually angular creatures. Our eyes are not designed to see lengths and velocities. We are designed to see angles. You don't think that? Think about this thing. Let's say in front of you, you have your laptop or any building or something. Take your finger and put it in front of the eye. You will see the finger is bigger than that laptop and the finger is bigger than me also. Isn't it? You can put a finger in front of your eye and the building in front of your house will be smaller than your finger. You know how big is an aeroplane, right? But when it flies, why does it look so small? So the thing is, you're never looking at the length of an object. What you're looking is the angle subtended. So if you have a tree which is 10 meter tall at a distance of 100 meter, right? And if you have a tree which is like 1 meter tall, which is at a distance of 2 meter, this tan theta is 1/2, this tan theta is 1/10. The 1 meter tree will look bigger. Try to look at your nose. Your nose will look like big, like a frog. You can't focus on your nose, but if you try to see, it looks pretty big because the angle subtended is more. So what you're actually seeing is always the angular velocity. You're never looking at the omega. So that is the reason the tree which is closer will look it is going faster compared to this. Is that clear, everyone? And multiple things. Did you ever notice your cycle when if you are riding a cycle, did you ever notice the front tire? Sometimes it feels like it is going front, sometimes it feels like it is going back. Did anyone notice that?
Yes, sir.
Right. Is anyone's fan is on right now? Can you put your camera towards the fan? There, Arya has kept the fan. Look at Arya ka video. Can you guys see that? Arya or Aditi, look at their fans in the video.
Yes, sir.
Which way are they rotating? दिख रहे हैं वीडियो कैसा देख रहे हैं? The fan looks like it is rotating that way, this way, that way, this way.
Yes, sir.
Can you see what is happening with the fan there?
How is it possible? Like, isn't it rotating only?
It is rotating that way, this way. It is getting messed up, right? So what is happening is the fan is rotating in one direction only. It is our eyes which are playing the tricks. The thing is, you need to understand human eyes, right? What we cannot see a video. What you think you're looking at a video is not a video. You're simply looking at photographs one after another. Did you ever play with that book? You know, you have a bunch of photographs and you flip the book, flip book. It feels like, you know, it's like a video. So a normal adult human being, right? We have around 16 FPS. That means if anything goes faster than 16, you think it's a video. You can't differentiate between two photographs. So in movies, normally they have 24 FPS. These are old movies. वो होता था ना reels. They used to call it 24 frames per second. So that means, let's say if I have to take a shot where I'm throwing my hand like this. So my hand motion from here to here, I'll take 24 photographs in 1 second. And when I play all of them in 1 second, it looks like my hand is moving like this. Whereas in reality, there are 24 photographs. Getting it? You must have heard about this thing, recently, like, 144 hertz refresh rate, 60 hertz refresh rate in phones. Heard these things? If you're buying a phone or something, you will hear these kind of terms. So now what happens is, think about like this. Let's say we got a rod. And let's say rod is rotating with omega. Now our eyes, right? Like I said, they can't see the video. What you're seeing is photographs. Now you tell me, let's say rod is rotating slower. So 1/16th of a second, basically. So every 1/16th of a second, you get a photograph. Alexa, stop. I don't know why this thing starts talking out of nowhere. So now think of like this. So you saw one photograph. Next moment, when you see the next photograph, let's say the rod is here. Now our brains, right? They're as lazy as us, right? They always try to find a shortcut. What do you think the brain will think? The brain will think the rod went from here to here. Okay. Now let's say rod is going a little faster. So one photograph, next photograph is this. What will your brain think? You went from here to here. Let's say rod is going even faster. Let's say rod comes here. So now what do you think the rod will think? Alexa, shut down. Why is this talking here? Suddenly I don't know where there's a ghost or something in the house. Just shut it down. I'm supposed to call Alexa, then it talks. This thing is talking out of nowhere. I think it likes circular motion. Anyway, so now you tell me, if the rod is rotating so fast, the rod actually went like this and came here. Now, what do you think your brain will think? Remember, it always likes to take a shortcut. It thinks you're rotating this way. You get in the problem there. Your brain will start perceiving the shortest path. You think it is rotating this way. If I go even faster, and let's say if I come to the same place, what do you think the brain will think? The rod is not rotating. It will think the rod is stationary there. So actually, if you can take your phone, you have some apps. You can make the frame rate of the phone equal to your fan car rotation. And when you put that video there, you will see the fan is stuck. You should try that and see. That looks kind of like this. Look at that video there. So what the cameraman did, the frame rate of the camera, he made it equal to the helicopter ka blades ka rotation. So every time you're taking a photograph, the blades are at the similar position there. So it feels like that helicopter ka blades are not rotating. You see the video again, the helicopter just looks like it is just going up. Niche to you can see water, boats, all are moving. Is that clear, everyone? So now when we are looking into your screen, that's what is happening actually. So when I say look at this camera, so sometimes the fan ka blade is here, so your brain thinks you're going this way. Sometimes the blade is here, your brain thinks it is going this way. So it feels like it is going front, back, front, back, front, back, front, back. It's messed up. So what is this refresh rate exactly then? Why do we need higher refresh rates for games? Again, the problem is this. When you look at old games now, we never had any problem. The problem started when we started having these eye graphic games and especially the shooting games. You can think about this. Let's say you're using a low frame rate, okay, 60 frames per second. What is the meaning of this? Your computer ka screen or whatever gaming ka screen is going to put 60 photographs every second. So you get a better clarity. Now, let's say you're playing a game where you take a big machine gun and you're shooting and you're running. Now think about this. So when the man is running, iska speed kitna hoga? Let's say he's going in a car or something, like 10 meters per second. But when you shoot a bullet, technically the bullet's ka speed will be 500, 400 meters per second. Is that making sense? Now, if you use a low frame rate, what do you think will happen? Now, in this bullet, right? Let's keep the frame rate a little less. Let's say you're using a frame rate of, let's say 40 or 50 frames per second. So that means every 1/50th of a second, you're going to take a photograph. In 1/50th of a second, this bullet is going to travel how much? 10 meters. Isn't it? So now if you play a game like this with a low frame rate, what will happen? when the person is running, you'll be able to see the person clearly. The person is taking the gun and running. But the moment he shoots the bullet, you will see a bullet here, then it will suddenly vanish. Then you will see the bullet again after 10 meters. Again, it will suddenly vanish. You will see a bullet again after 10 meters. Can you see what is happening? You get to see the bullets every after 10 minutes. The bullets will literally vanish in the middle because the frame rate is less. So the whole thing will start looking pretty messed up. So if you have a higher frame rate like 150, then you'll still see the bullets vanishing, but it happens at a lesser rate. So once you go into the programming, you will see a lot of things like this. There was a FIFA ka game, right? There is something called a physics engine. So you write a program which will actually obey all the physics laws and everything. So in that, right, you have to tell the program. So you have to keep on calculating, isn't it? In a computer program, if you hit a ball like this, how will the program know how should the ball travel in a parabola? So every instant the program has to do calculations, like mostly a millisecond, every millisecond. So these people found a glitch in the game. If you can hit the football at a very high speed, when the ball comes in front of the goalkeeper, right, there is a glitch in the calculation. The ball passes through the head of the goalkeeper and goes to the goal. So what was happening was the ball was here, the machine did the calculations. It takes a small pause of a millisecond. The ball is going so fast, it crosses the person. Then it does the calculation. So for that millisecond, the ball will ignore anything in the middle. So the ball will simply pass through the goalkeeper. That is a glitch in the game. You can actually shoot through the goalkeeper. And it is pretty easy to set. If the calculation is 1 millisecond, if you can make it 0.1 millisecond, now it will calculate at every point. Now the goalkeeper will block the ball. You're getting this? So a lot of stuff. So when you're designing games, you need to know a lot of stuff. Like, you need to know how things work. Anyway, that's a bit about it. So let's take a small break. Come back by 9:40. We'll continue from here. We'll see more problems on this. See one more. Chalo, comes on everyone. So let's say we have a laser here. So this laser is shining a light. That is point P. This angle is theta, and this laser is rotating with omega 0.1 radian per second. You're getting what we did? So you took a laser in your hand and you're just rotating your hand continuously. So the spot is continuously moving. So after some time, P will come here. After some time, P will come here. So P is continuously going up. Let this distance be some D. So P is the laser ka. It's a laser light on the wall. Or you can say laser spot on the wall, whatever you want to call. Find the velocity and acceleration of point P when theta is 60 degrees. Is the question clear, everyone? When theta is 0, the light ka spot will be here. Theta 10 degrees here, 20 here, 30 here, and so on. This thing is continuously going up. So the point P is moving. Find the velocity and the acceleration of point P when theta is 60 degrees. Let's get this. There you can see we are just playing with one definition. Omega is d theta by dt. After that, it is all standard kinematics and all that stuff. Right, Samyak. Yeah, I can give numbers like let's make this 100 meters. Find the velocity and acceleration in theta is 60 degrees. Try, everyone try. I'll give you 2 minutes. 0.4d, 0.8 root 3d, velocity 2 meter per second, 100 secant square omega. Theta is given, right? You can use the numbers. 400. Okay. Let's see the speed part. So let this thing be y. So basically, velocity of p is nothing but the rate of change of position. So this is velocity of p. So velocity of point P is nothing but rate of change of y coordinate, because when P is moving, what changes is the y coordinate. Great. So tan theta is equal to y by 100. So y is equal to 100 tan theta. Differentiate both sides with time. So this will be dy by dt. 100 is constant. Tan ka differential is x square theta. Then we have d theta by dt, which is nothing but omega. So this will be 100. D theta by dt is omega. So that becomes 0.1. So that is 10 x square theta. There, this is your velocity of point P. You want acceleration? Differentiate again. dv by dt 10 sec square ka theta differential 2 sec theta. Then differentiate sec theta again. So we remember chain rule. This will become acceleration of point P. This will become 20 sec theta. Sec theta ka differential is sec theta tan theta. Again d theta by dt. So yep, that would be your acceleration. 20 sec square theta tan theta into omega. This is your velocity. There, numbers are given, you can substitute there. Theta is 60 degrees and omega is 0.1. Put it there, you'll get your answers. Is this clear, everyone? So velocity would be 60 degrees, na? So cos 60 is off, that will be 40 or 400. 400, right? Or is it 40? 1 by 4, 40. And what about the acceleration of point P? And that will be 2, this will be 4, and tan 60 is root 3, 8 root 3. Someone got it. 0.8 root 3d. I think same thing, I guess. You just kept everything in d there. Won't velocity be d theta by dt is omega, na? This is 0.1. So 100 into 0.1 is 10. Any doubts on this? Clear? Let's see one more. Let's say we have a hemisphere. So we got a rod like this placed on top of an hemisphere. This point is hinged. Matlab, the rod is fixed on one end. This is radius r. This is theta. So someone started pulling this hemisphere with speed v. So now this hemisphere is pulled with a constant speed v. Find omega at this instant. Find angular velocity of the rod. So you can ask yourself, so what happens if you look at the picture here? This is how it will look. So after some time, so here this was the hemisphere. This was the rod. After some time, the hemisphere will move somewhere here. The rod has become something like this. So you can clearly see the angle is changing continuously. So if theta is changing, that means there is an angular velocity. Find the angular velocity of the rod at this instant, or when the angle is theta. V sine square y r cos theta. That looks right again. Try others. So every time that is the same story. Somehow you need to get that theta there, and then you need to differentiate, and you need to relate everything to that velocity and radius and stuff. Let's see. So basically, you always have to create that variables. That is the most important thing. So when you start pulling this hemisphere, what changes? This distance changes. Let this be x. If you think about it, this rod is nothing but a tangent to the hemisphere, isn't it? This is 90 degrees because it's a tangent. And this is radius r. So you're done. What is sine theta? Sine theta is opposite side, which is r by hypotenuse x. And what is dx by dt? Dx by dt is the velocity of the hemisphere. Differentiate on both sides. Why do we need to differentiate, or else you won't get d theta by dt? Sine ka differential, cos theta, d theta by dt. R is constant, you're differentiating 1 by x. So minus 1 by x square dx by dt. X power minus 1 ka differential, everyone. This much differentiation should be able to handle. You're done. So d theta by dt is omega. This would be minus r by x square cos theta, and dx by dt is nothing but a v. And substitute there. What is x? X is nothing but r by sine theta. Minus rv, r by sine theta. So that will become r square cos theta sine square theta. The reason you're getting minus n is because theta is decreasing. Minus v by r sine square theta by cos theta. if you see, right, technically, once you write this statement and you differentiate, physics got over. It's all math. You need to figure it out. You should have seen few models. Clear with this? Any doubts on this? Dear.
So we could have done this using like the wedge constants which you taught, equating the velocity along the normal.
वो भी कर सकते हो.
उससे डायरेक्ट v by r करना है, I guess.
But उसमें problem ये होगा ना. Then मतलब वही end of the you need this length then.
That we can find by as we are given
Geometry से
theta, right?
करेंगे. हाँ. सही है वो.
Yes, sir.
Let's see one more. You can see all these questions like 3-4 steps. Little calculus is involved. Again, I didn't teach you anything. The whole thing I taught you today was omega is d theta by dt. We're just playing with that. So let's say we have a fixed ring. Radius is r. So on this fixed ring, you have a rod. And this rod is moving with speed v. So P is the point of intersection of the rod and the ring. So that is how P is defined as. So at some point here, if you observe, this is theta basically. So see, this is what is happening. If the rod starts moving, how will the picture look like? Initially, the rod is here, then the rod is here, then the rod is here. So where is point P exactly? Then point P will be here, then point P will come here, then point P will come here. So for anyone who's looking at this point P, how does the motion look like? Doesn't it look like this? This is the vector. This is the vector. This is the vector. Isn't point P rotating? Is that making sense? It feels as if the point P is moving on a circle. Is the scenario clear, everyone? So we got a horizontal ring, right? So the ring is on your table, right? And you have a rod which is sliding on the ring. And we have defined point P is a point where the rod and the ring intersect. So when the rod comes here, this becomes point P. When the rod comes here, this becomes point P. Are you getting it? So that is the definition of point P. P is a point where they both meet. So when you're sliding the rod, the point P will feel like it is going on a circle. So P is actually moving. So that means it will have an angular velocity. Find omega of point P at theta. Is the question clear, everyone? Anyone didn't understand the scenario, please ask me. And others, do keep your cams on. Shaunak, Shaurya, Shayan, Vanchika, cams on, everyone. नहीं रे यार. Right, Siddesh. Anyone didn't get the picture, please ask me. These questions are important. These are all proper mains level questions. Because if you actually know what to do, it will not take more than a minute to solve. It's always about somehow finding the theta in terms of x and then differentiating. That is a theme in all these questions. Right, Ishman? Let's see. Nee, Samyak. Nee, Raditi. V sin theta by r. Didn't you type the same answer, Arya?
I'm getting the same thing.
You typed it twice, even after I said it is wrong. Okay, listen. So the thing is, how is point P actually moving? So P is actually going like this, isn't it? So if you take components, need to understand the point P on the rod is going this way. So uska component will be this. But like I said, now when you take components and all, it gets really confusing. So I always prefer that angle things. Like I keep saying, exam mein, there's a high chance you'll goof up something. So this is X, this is theta. Simple. So this is your point P. This is your radius R. What is cos theta? X by R. Differentiate on both sides. This will be minus sine theta d theta by dt. This will be 1 by r dx by dt. What is dx by dt? That is nothing but velocity of the rod, because this rod is going with v. And what is d theta by dt? Omega. So this will be minus u by r sine theta. Bas itna hi tha. Again, we got a negative sign because theta is decreasing. Clear with this? So actually, you can write like this. Omega is minus d theta by dt, since theta is decreasing. So I can keep the magnitude. Clear with this? See where it went wrong. I can ask you for acceleration, then you double differentiate it. But yeah, story is the same. See, it became so easy compared to the previous one. This is still easier. Any doubts on this? See, the sine theta should be in the denominator. Sine theta को नीचे लेके आए and you made it cosecant theta. What are you doing, Ray? Why you want to do with components? It's messed up. So when you take the velocity, the point P actually is going which way? See, again, remember, point P is on a rod. That is an intersection. This is going this way. Right? So how do you take the components for this? So the P ka velocity which is going this way, we should take it the other way around, I guess. P is going on a circle. So this is the velocity. So for this, that will be the component. You have to get that angles there. Aditi, you're saying something?
No, I was just gonna say that I got till u by r sine theta, but I kept it in sec theta and tan theta terms, and then I realized that I spoke too soon. So please continue.
Well, like that. So basically, you have to divide that only, right? So, देखो ना, how will you get that component? So this v का component should take in this direction. So you get the angles. So it is always that only. Like you need to figure out how is that velocity moving. It can get confusing. Like when you take that component, that's what I'm saying. Sometimes it will click, sometimes it doesn't click. I won't take that risk. I get confused. So you guys take a call on that. Next thing. Sometimes the component thing looks easy to see. In this case, I think it is you have to divide the component of this guy. Actually, if you see what is point P, P is actually going in a circle only. So this is VP. And we know this component is V. So VP ka component is that V. I think so VP sine theta is V. So we get VP is equal to V by sine theta. That by r will give you omega. Right, Obvia? Because see, what is P? P is definitely going on a circle, isn't it? So that is the actual velocity. And at that instant, the peak of velocity at that point, horizontal component is V. P is not going in a straight line. P is going in a circle. So peak of horizontal component is V. But I'm telling you that gets very confusing. That's the reason some of you are getting that answer sin theta upper. So unless you're pretty confident, then it is fine, or else stick to this. Next thing. We have three particles, ABC. Going with U, B is going with U. We have done this in kinematics, C going with U. Equilateral triangle, side A. So you know the story. A, B chase each other. With speed U. Who is the centroid? So this is how they go. Right. So if you actually look at this position A, so if you're looking at point A now, this is what O will think about A. This A is going something like this. It's going in a spiral. This is the trajectory of A as seen by O. That means at any time, if you look at the reference line, this is theta. This will be your angle theta. So the theta is continuously changing. So when A comes here, this is the theta. When A comes here, so theta is continuously changing. Find theta as function of time t. I can also ask like this. This triangle is actually rotating with a continuously rotating. Find the angle rotated by the triangle after time t. Or find the time taken for the triangle to complete one revolution. So we can play anything. Find the angle rotated by OA bar vector in time t. Is this making sense what I'm asking? So if you look at this picture here, this is the centroid. Initially, let's say A was here, then A came here. You can clearly see how is the angle changing. So this thing is continuously rotating. So there is an angular velocity. Find the angle rotated by OA at time t. Let's see how you handle. Now this becomes an advanced question. You combine all this thing. Now this becomes a question from what? Kinematics and circular motion ka combination. In case you forgot, you should definitely go and refer that with this in relative motion. This was the question. Page 228. Now, in case you're wondering exactly what the hell is happening here, let me help you a bit. If you see the explanation, this is the explanation I gave for that day. I said at any instant, if you look at the velocities, there are u cos thetas which are pointing towards the center. And we did the problem, right? And then I also read some statement here. See, what are the u sin thetas doing? U sin thetas are responsible for rotating the triangle. So in kinematics, u sin thetas were useless. We didn't care, but now we need it. The u cos 30s are bringing them closer towards the center, and u sin 30s are rotating the triangle. So u sin 30 is your tangential velocity. Have a look at this picture once. Let's see, how will you handle this? How do we start? Ln d by √3. नहीं रे, dimensions match नहीं हो रहे हैं ना. ln के अंदर it should be dimensionless quantity. ut √3 by नहीं समझा. You'll get in terms of ln. Let me help you with this. Like I said, the question is find angle rotated at time t. That itself is a big clue. Matlab, you need to integrate. That means the only term which can give you theta in terms of t is omega d theta by dt. So we need to get omega. So let's see the story again. So we know when these three particles are moving towards the centroid, if you resolve the velocities, so this is u, this angle is 30 degrees. You will notice this component will be u cos 30. This component will be u sin 30. Same story. So this will be u cos 30. This will be u sin 30. So here u sin 30 is responsible for rotating and u cos 30 is decreasing the distance between them. So this is O and this is A. So here u cos 30 is decrease the distance. Right. So what is the OA ka initial value? OA initial value, remember, it is 2/3 of the height. A centroid divides in the ratio of 2:3. That will be 2/3, and the height of this thing is √3 A by 2, which is A by √3. So what do you think after time t, what will happen? Now look at this. This is O, this is A, and you're going towards this with u cos 30. So the distance won't remain constant. Distance is changing here. So OA final will be A by root 3 minus U cos 30t. Because after time t, you will travel a distance of U cos theta t, and this will be the new distance. So here people, omega, when you write V by R, here V is not changing, R is changing in the denominator. The reason omega changes is because of the distance and not the tangential velocity. So we get OA final will be A by root 3 minus U root 3 by 2t. So cross multiply this, and this will be 2A minus 3U by 2 root 3 into t. And if you remember, the mains question was this: find the time when they meet. When they meet, what will happen to OA final? 0. That will give you the time directly. There you got OA final. And so what is omega here? Omega is nothing but V tangential by OA final. So V tangential is U sine 30. And your OA final is this: 2A minus 3UT by 2 root 3. Have a look at this. So if you got till here, I think then your job's done. We can solve it. Any doubts still here, please ask me.
Sir, how did you get that OA final? O A by root 3 minus U cos theta into t.
Distance into time. So after time t, you will travel this much distance, U cos theta t. So subtract that from the initial distance. Right? From initial distance, if you subtract U cos theta t, what do you get?
Yes, sir.
Sure.
Yes,
This
sir.
is initial OA, na? So after time t, you'll travel U cos theta t. So subtract that.
Yes, sir.
So then let's simplify this. So we get omega is equal to U sine 30, that is U by 2. The denominator is 2A minus. Technically physics got over here. So this will be U root 3 by 2A minus 3UT. Omega is d theta by dt. It might look a little scary, but it is actually a decent integration. So this will be d theta. This will be U root 3 dt by 2A minus 3UT. Integral. This will go from 0 to theta. This goes from 0 to t. Now, in case you forgot how to integrate this, I told you I'll show you all these ln integrations whenever they come, at least till next year. So this is the integration. So dx by ax plus b ka integration is 1 by a ln ax plus b. So in our integration, if you clearly see dx by minus 3ut plus 2a. So this a looks like minus 3u, and here this thing looks like that b ka term. So if you integrate this, 1 by a, that will be minus 1 by 3u ln minus 3ut plus 2a. I hope you can see that thing. So then integrate this. So this will be theta. This will be U root 3 minus 1 by 3u. This much integration should become comfortable. Minus 3ut plus 2a. Limits will go from 0 to t. That would be minus 1 by root 3. Put the limits there. Ln 2a minus 3ut. Then put 0 there. You'll get ln 2a. Ln a minus ln b, ln a plus b. So you'll get theta is equal to 1 by root 3. Send minus inside. You'll end up with ln 2a by 2a minus 3ut. Check. That's your theta as function of time t. Yeah, there's a lot of maths, but that is how the question will be framed.
So
Yeah.
Sir, I think there will be a constraint on the value of u, I guess.
This only, no? The time should be less than 2a by 3u.
Because if it's not, then the log
That
will
is when
become
they'll meet,
negative.
na? 2.2 by a. That is the time when they will meet actually.
Oh, right.
Hmm.
Yeah, they meet at right.
So after that, it is gone. They touch, so it is done. Again, see what we did. The same story. This is the same story we did in kinematics. There are two velocities, u sine 30, u cos 30. U cos 30s are bringing you closer. Srihari, that you understood, na? Initially, distance was a by root 3. So after time t, you will travel u cos 30t. So the distance will decrease. So this distance was initially a by root 3. So from that, if you subtract u cos 30t, that will be the remaining distance. So we got OA final. So here what was happening is when you're at omega v tangential by OA, v tangential is constant. At every time it is u sine 30. The problem is the distance between them is decreasing. So here omega is changing. Once we got omega, this page is completely max. Once you defined omega, physics got over. Clear with this? There is something more I can ask you in this question. I can ask you find the acceleration of the particle at time t. So that, listen. Now here, even though the speed is constant, the direction is changing every instant. Now here in this case, the speed of the particle is constant. So let's say in small time dt, so initially it is, let's say, going with velocity v. In small time dt, this particle velocity will change its direction by d theta. So meaning when you look at this particle chasing, actually, this is how it looks. Initially it is going like this. After some time when it chases, the particle velocity will become something of this sort. Again, I'm exaggerating it, but it will be pretty close to this. This is your v initial, which is v, and let's say this thing rotates by a small angle, d theta. I'm just exaggerating this. This is v final, and both the magnitudes are same. And we know what is the change in velocity? Change in velocity vector is nothing but v final minus v initial. So from triangle of vectors, if you join them, you will get this. So v final will be delta v plus v initial. So if you join from head to tail, the resultant vector must be delta v. Now you can clearly see this is an isosceles triangle. This is v, and this is v, and this is delta v. So from the center, if you drop an angle, this will be d theta by 2. Again, these angles are quite small. D theta by 2. This can be written as sine d theta by 2 is equal to delta v by v. So this piece also will be delta v by 2 and delta v by 2. And we know for small angles, you can actually say it is an arc and finish it off, but okay. For small angle theta, we wrote this last time if you remember, sine theta becomes approximately theta. And d theta by 2 is very small. This will become d theta by 2 is equal to, and write it as dv because I'm using d theta. This will become dv by 2v. So from here we get dv is nothing but v d theta. Now if you put dt on both the sides, So we get acceleration is v into d theta by dt. And what is d theta by dt? Omega. There, it's a pretty good result. So in this chasing particles, whenever they ask you find the acceleration, it is simply velocity into omega, speed into omega. And what is omega? This is your omega. This is your omega. So if you multiply this with speed u, you'll get the acceleration at time t. We could have done this faster without that. You can say this is v and this is v. Since this d theta is very small, this thing is like an arc. So this length will be v d theta, which is nothing but dv. So we get dv is equal to v d theta divided by dt divided by dt. This becomes acceleration is equal to v omega. There. That also works pretty fast. Since theta is very small, you can treat it like a small triangle or you can treat it like an arc. Both work. But is that formula clear, everyone? So based on that, you tell me what is the answer for this then. Let's say we have 4 particles chasing each other. B is going with you, A is going with you, C is going with you, D is going with you. Square of side A, B, C, D chase each other. Find the acceleration of A at t is equal to 0. If this is a paragraph question, I'll ask you these things only. Find the angle rotated and find the acceleration of the particle. Find acceleration of A at t is equal to 0. Speed is constant, but the direction is changing. So if you look at the trajectories, this is how it looks. There. Particles on a square will chase each other like this. Let's get this. Should definitely go back and revise this once in the kinematics. U square by A, okay. Root V square by A, okay. Try, I'll give you a minute more. Just now you got the formula V into omega. So your job is to get omega. If you can get initial omega, my job's done. U square by A minus, no, I'm just asking your time t only now. Let's see. Again, same story. All the particles are trying to go towards the centroid. So if you resolve the velocities, this is U. So one component is trying to go towards the center, one component is tangential. So luckily this is 45. So this is U by root 2 and this is U by root 2. This is your V tangential. The distance is changing. I agree. You can calculate that. So omega at t is equal to 0. Omega is V tangential by this distance. It's an half diagonal. What is half diagonal? A by root 2. Which is U by root 2, A by root 2. Which is U by A. Isn't it? And what is the acceleration? V into omega. V is also U, omega is U by A. So U square by A. Check. All right, Utsan. Right, Arya. Clear with this? This is your distance, everyone. This is your r, which is a by root 2, half diagonal. Clear how to get that omega part? There, this is a pretty good one. You can play around a lot of things, huh? Find the time when the triangle is rotated by 180 degrees. If it is 180 degrees, you just need to put theta is equal to pi, you will get the time. Find the area of the triangle at time t. You can ask a lot of things. Acceleration of the particles, time when the particles meet, distance traveled by the particles, draw the trajectory, and so on. There, if you see today, we are all playing with omega only. We didn't do anything else. So next class, when we catch up, we'll continue from here. We're going to see more. Omega ka, there are 1 or 2 more variations, and then we will see angular acceleration, and then we'll see some circular kinematics problems, and then we will go for uniform circular motion. So this is a little non-standard part. Rotation means it's not always, things will go in a circle. You can have things going like this also. Okay, that will wrap up for that day, right? So do finish your friction curve solving. Whatever you're solving, do complete it as soon as you can. So with that will wrap up for that day. There is a test online till night, till 11:30. Hope everyone has given it. In case you're not given, so do make sure to give it. So any doubts, anything, please stay back and ask, or else you're free to leave.